Cool. All right. Today we're going to be still reviewing kind of this, a little bit of the stuff from geotech. You remember last Wednesday, we were going over the volumetric stuff and the void ratio, porosity, and all that stuff. The reason we were doing that was because you'll see those index parameters in the design equations that we use. So again, just to bring you back to geotech, if you remember in the geotech class, we talked a lot about geology and how important geology is with geotechnical engineering. The issue with geology, though, is the majority of that is a qualitative, like, science. So it's a lot of observations and, like, just understanding the physical characteristics. But us as engineers, we add that technical aspect. So we need to assign numbers to that. We need to use our fancy math equations so we can predict and create models and understand the mechanics behind how soil is going to behave. So in order to do that, we need to assign number values, and that's where these index parameters come into play. So instead of observing a sand and say, oh, look, it has a lot of voids in it, a qualitative observation, we can then assign a void ratio to it, which then we can use to predict the behavior. So we're going to review a little bit of that today, and then we're going to also talk and review the stresses in soils, so the in situ state of the soil. And this is all going to be stuff from the geotech class, but again, this is going to be the important things leading into the design of foundations and other geotech structures. Any questions so far before we get started? No issues with Canvas or anything with the quiz? Sweet. Okay. So no, don't do this. All right, got to be pressing this here. Yeah, so these are the resources we're going to be pulling from today, chapter 6 and chapter 2. If you're able to find any of these online, if you are still looking for resources or where to find these, let me know and I can send you links or whatever. But these are floating out there somewhere on the internet, and you guys can find those. So from last week, we went over the importance of density, the 3 states of density based off of the moisture, the natural state, the dry state, and then the saturated state. We also talked about the mass relationship that's really important, called the moisture content. Does anyone remember what's so special about the moisture content, or what's like that weird little caveat like thing we have to check out for the moisture content? I'll give you a hint. It's multiplied by 100%, but yeah, it can be over 100%. So keep an eye out for that. We have the 2 or the 3 volumetric considerations of void ratio. This is in decimal. Porosity, this is in percentage, and this porosity is 0 to 100%. So this is a normal percent. And then degree of saturation, same as porosity. This is 0 to 100%. So again, the moisture content we have to watch out for, because this can be greater than 100. So we went over the phase diagram. And if you remember in geotech, we kind of focused a lot of this at the beginning of the semester of geotech, understanding that although soil is a mixture of components, we can summarize it into a weight and a volume of solid, a weight and a volume of water, and a volume of air. So we have the solid portion, the water portion, and the air portion. So before we get started on this week's stress stuff, let's just go over an example illustrating how to find some of these important material properties and index parameters. So once you just imagine that we go outside, we dig a hole, and we pull out 45.6 pounds of just moist soil. So wet soil, natural soil, there is water in it, there is solid in it, and there's air in it. We're able to calculate the volume of that soil that we took out, and it's going to be 0.4 cubic feet. After the sample is 100% dry, so we place it in the oven for 24 hours, we bring it out. We see that its new weight is 37.8 pounds, and we are told that the solid specific gravity, that GS value, is 2.65. So from just going out, digging a hole and taking that samples, let's see if we can find the moisture content, the unit weight, and the dry unit weight and the void ratio of that. So first, what we're given is the Make sure I'm in the right spot. Yeah, so what we're given here is we know that in its moist state, and again, I apologize for using that word, but in that moist state, we have two things that have weight. We have the weight of water and the weight of the solid material, right? Because the weight of air is 0. So for that, we're told that it's weighing 45.6 pounds. We're told that the volume is equal to 0.4 cubic feet. And again, I'm not going to put a T, but technically this is volume T, so the total volume here. Just anytime you see just a normal V with no subscript, just know that that's the total volume. And then we're also told that when we take the sample out of the oven, assuming all that water evaporates and is boiled off, then what we're left with is only the weight of the solid, which is equal to 37.8 pounds. Right. So from that, if you remember from the geotech lab, we did this, and the CE materials lab, we did this too, to find that moisture content. If we know the weight of the solid and that we know the weight of the solid plus the water, then simple math, we just subtract those two and we can get the weight of the water that was in our sample, right? So 45.6 minus 37.8, that's going to give us our weight of the water, and that is 7.8 pounds. So if you remember from geotech, the whole purpose here was to fill out all of these little sections, all of these little phase diagrams, and whenever we fill out all of these little aspects, the WVs, the Ws and the Vs, then we can plug them into our equations for moisture content, unit weight, void ratio, all that fun stuff, and it makes life a little bit easier. So knowing all of those things, we can already calculate the moisture content really easily. If you remember the moisture content, this is shown by like a little fancy W, like a sideways italicized W. So for the moisture content, we know that that is the weight of the water divided by the weight of the solid portion. And then we multiply that by 100 to put it in percent form. So previously what we just found was we had 7.8 pounds of water and then 37.8 pounds of solid material. Multiply that by 100 and we get 20.6%. So again, what's helpful here is to ensure that you are canceling out these units. You know, it should always be a weight over a weight or a mass over a mass. You know, if we were working in SI units, that could be like grams or kilograms. As long as those two cancel out and it's either a mass or a weight, then it can be used for the moisture content. So the unit weight, just the normal unit weight, that's shown by the gamma. And what this unit weight is telling us is, since it's not described as either saturated or dry, what we're saying is just in this natural state. So whatever we have here. So all three aspects of it. So we're going to have the two things that have weight. So the weight of the water plus the weight of the solid, and then divided by the total volume, or volume T there. So again, just thinking of like anything, all things have a density, all things have a unit weight, like this table or whatever this is, takes up a certain amount of volume and it has a certain weight. So what we're finding is the weight divided by the volume, and that's the bulk unit weight. So for that, we can plug everything in. We know that it was 45.6 pounds was the total weight of the water and the solid, and then the total volume was what, 0.4 cubic feet. And so this is equal to about 114 pounds per cubic foot. So PCF, pounds per cubic foot. Who remembers the two extremes, like to keep an eye out for when we're calculating these? Like what should this value never be lower than?
Lower than water.
Yep, yeah, 62.4 we know is the unit weight of water. If you don't have that drilled in your brain already, definitely, you know, put it above your bed or something so you wake up and see it every day, because you're going to use that a lot in the FE, the PE. You know, it's not worth looking up that every time. Yeah, on the other extreme side of things, like, yeah, concrete, which is close. Yep, 150. Yeah, 150 pounds per cubic foot is concrete, and we can all picture what concrete is. Maybe you've picked up a piece of concrete. It's really dense, and rarely do we see soil that has a lot of air in it, denser than concrete. You know, if you get into rock mechanics and you're working with like granite and other types of like massive rock forms, then maybe you'll see it above 150. But for this class, anytime we're working with soil, just double check your calculations, make sure it's somewhere between 62.4 and 150. You know, make sure it makes sense before writing it down. So the other thing we can find too is that dry unit weight. So that's just going to be the gamma dry. So for this, what this is just the weight of the solid divided by the total volume. So this is whenever all the water is evaporated out. So we were told that number to 37.8 pounds divided by 0.4. And then this is 94.5 pounds per cubic foot. So you could do it that way. If you remember, we also showed some shortcut equations last class, where all these volumetric like values are related in one way or another. So another thing that would be helpful to memorize, again, for the PE or for the FE, is this relationship here. 1 plus the moisture content. So this one right here, this is the dry unit weight is equal to the natural unit weight or the moist unit weight divided by 1 plus the moisture content. And we can just do the math real quick and double check, see if this works. But we'll see 114 pounds per cubic foot divided by 1 plus 0.206, since this has to be in decimal when we're doing math. So we show it in percentage in our reports, but when we're doing the math, we bring it back into decimal side of things. And we can see that this is the same value, 94.5 pounds per cubic foot. So these will be helpful if you work in geotech. Again, the FE section, just being able to recall or even to just check your work quickly. You know, you could do it this technique using this equation and then applying the other one just as that confidence factor to ensure that your calculations are all set. Okay, so what we need to do now is find so we've already found the dry unit weight. We've already found these. Only thing left to do is find the void ratio. Sorry, let me go back to the other color. The void ratio, remember, is E. Who remembers what the void ratio equation is? Yep, volume of voids divided by volume of solids. So again, two volumes, they cancel each other out. We show it in decimal form, and we show it using an E value. So we don't know the volume of voids and we don't know the volume of solids. What we do know is the weight of solids. We found that already at 37.8 pounds. And we do know the specific gravity of the solids of 2.65. So again, that specific gravity and just density in general is going to be that translation tool that gets us from volume to weight or weight to volume, back and forth. So what we know is about the unit weight, the specific gravity is equal to the specific gravity of the unit weight of the solids divided by the unit weight of water. So the unit weight of solid is going to be equal to the weight of the solid divided by the volume of the solid, and then again, divided by the unit weight of water. So what we can do now, since the way fractions work, it took me a while to really grasp this, but again, like if you have a fraction in a fraction, then this, let me just highlight it so it's not crazy colors. So this is going to move into the denominator. So what this equation can be simplified for is something like this. So luckily we know the specific gravity, GS, we're told that, right? 2.65, we found the weight of solid. And we know the density of water, so now we can rearrange this equation to calculate the volume of solids, which we need for our void ratio. So again, volume of solids, then what this equation is going to equal after we rearrange it, something like this, and we know all of these. So 37.8 pounds divided by 2.65 times 62.4 pounds per cubic foot. Again, for this class, like I'm going to use most of the time US units because most of you, I'm assuming, are going to be working in these units like in the future. But I will still have some examples in SI units because the FE and the PE use both. So if we're working in units like pounds and cubic foot, then we're always going to use 62.4 pounds per cubic foot. SI units, it will just be one, right? The unit weight of water is 1 gram per cubic centimeter or 9.81 kilonewtons per cubic meter. So try to make sure and when you're going through these problems in the class and on any of the tests that you end up doing, like PE especially, you get kind of used to working quickly. Just always highlight or circle the units like when you're reading the equation, so you know that your answers are going to be in the correct ones. So anyways, this stuff will go a little bit quicker because this is probably all familiar to you guys. VS is equal to 0.23 cubic feet. We know that the total volume is equal to the VS, the volume of solids, plus the volume of voids. We also know that the volume of voids makes up the volume of water plus the volume of air. So basically what we can do for the volume of water is the same thing as before. So we'll use the same equation here, since we know the weight of water. So the volume of water is equal to the weight of water, weight of water times the GS times, technically this should be GW, I guess, the specific gravity of water times the unit weight of water. So the specific gravity of water is 1, since it's a reference to itself, 7.8 here. Again, this is pounds per cubic foot. So the pounds cancel, cubic feet is left, and we get a volume of water equal to 0.13 cubic feet. So now we can start plugging everything in here that we need. We have the volume of water being 0.13, solids from before 0.23, and we know the total volume is 0.4 cubic feet. That's what we were told before. So now what we need to do is just find the volume of air, and just by subtracting that out, volume of air is equal to 0.04 cubic feet. And that is equal to 0.17 cubic feet. We know everything. Sorry if that's a little low. We know everything now to plug in for our void ratio. And this will be 0.17 cubic feet divided by the volume of solids at 0.23 cubic feet. And we have a void ratio of then what? 0.74. That will be our void ratio. So again, this is hopefully a little bit familiar to you from the geotech side of things. If it's not though, work through this again slowly and let me know if there's, it's not clicking or you're not getting it. I can give you some more example problems because understanding how to find these are going to be an important thing into setting the picture for our design eventually. You're going to be given soil conditions. We're going to need to find these index parameters and these unit weights. And then from those unit weights, we're going to then learn how to design the foundations and stuff. Let's throw in one more. Like, let's say we wanted to find the degree of saturation too. That was another important one that we'll see. The degree of saturation. Actually, well, let's see. Before the degree of saturation, there are also some other equations, if you remember, for that void ratio on the back. So another shortcut equation is this one here. This was also from geotech, but this is a volumetric relationship. Again, since they're all based on the same thing, the void ratio can also be expressed as a function of the specific gravity, the unit weight of water, the dry unit weight, and then this right here, very important. Don't forget the -1. It's really easy to forget that. But in this equation, then we can plug everything in that we know, and we see that it's basically the same thing at about 0.749. A few of the rounding issues there. So like, unless you're really comfortable with all of these steps, what I would recommend, again, like if you have the time, then double check, like using both of the equations. On the FE, for example, you'll probably be given this equation somewhere in your handbook, but you'll also be given the void ratio, or the equation, the volume of voids divided by volume of solids. So if you have time, then double check it and just make sure that those two equal. So you can have confidence in your answer for that. All right, so we know the degree of saturation is also the volume of water divided by the volume of voids. Sorry, the volume of voids, right? But then there's another equation that is super useful for this. That's kind of a shortcut. Does anyone remember that saying, or the thing we talked about last week? Yep, yeah. Soil engineer equals George Washington, or whatever you want to use to remember it. Again, I don't know why it like stuck in my head as sewage, just seeing it as SE equals WG. You just spell out sewage and that works somehow. But we could also do this math since we have everything. And then solve for one of those. So this is probably one of the most easy or important relationships equations here. That will save you a lot of time on the FE too, to know that one. So that is how we could find the degree of saturation. And again, just to double check, just to show and go overkill here, there's also this relationship that we could use to double check or find our saturated unit weight. And this is a function of the void ratio. And if we did this out, we would see about 121 pounds per cubic foot. So again, what we talked about last time too, like do a mental check when you're calculating these. Your dry unit weight should always be the lowest number. Your natural unit weight should be slightly larger, and then your saturated unit weight should be the largest number, right? Because we're adding water each time, we're adding mass, but the volume is staying the same. So keep that in mind too. Okay, so from last week, we kind of left out on this stuff. We had like, okay, this is important, like, because you're going to be given a design scenario. We take a cross section of soil at a site, and let's say we wanted to build something like a tunnel or a utility pipe or something in this like underground scenario. Just like if you were swimming in a pool, or if you have ever dove before, like the deeper down you go in water, right, you feel more pressure. You can probably look up videos of like people like taking a water bottle or a can or something and just putting it under like 10 feet of water, it ends up crushing it. So even though it's a little hard to imagine because we don't swim in dirt and soil, but if you were to somehow magically swim 10 feet down below the earth, like you would feel the same pressure. Like it would be the same thing as you would at the bottom of a swimming pool. So at this, if we were going to be constructing this tunnel or whatever the heck this is, mole people home, then there's going to be some stress. And remember, we call that, like, we show stress as a sigma, a lowercase s. And those in situ stresses are important. So that's what we're calling this, the in situ stress. And that just means in the natural state or in its natural condition. So understanding how that those stresses are based off of the soil above it is super critical in geotechnical engineering for designing structures, but also for understanding geologic formations as well. And what we'll see like in the class is, and what we're talking about like this week and next week is if we were to put like a foundation and that foundation is loaded by the structural, the high rise above it, then these stresses are going to dissipate underground and it's going to cause additional stresses on top of that, right? And that's what we called in geotech our delta sigma, our increase in vertical stress. And that's really the thing that's important for us. If we have an existing structure underground and it's designed for a certain overburden pressure, a certain sigma, but then 20 years later, we come and decide to put a high rise right next to it, then that is going to affect the stress conditions on our object. And it could either exceed the capacity or it could exceed the capacity of the soil and so on and so forth, and we could have issues. So understanding that distribution of stress as we go vertically from the natural in situ state, but then also at the loading state, the P value, then yeah, that's really important. Do you remember I had like on the exam, there was like Urban Meyer, that didn't last long. A little example with Urban Meyer there. But anyways, so after today, just a little checklist of everything. We're mainly going to be focusing on stresses and reviewing that. So by the end of the day, you should be able to calculate the in situ stresses in the soil mass, and that's from the unit weight. You should also be able to explain the differences between the effective stress and why that's important. So if you don't remember that from geotech, don't worry, we're going to review that. And also determine the pore water pressure in different static and dynamic scenarios. So especially in Florida, this is really important. We have a groundwater table that's really easy to find, right? You just go out in your backyard and dig a hole, you'll find the groundwater table. We also have an aquifer system, which is really helpful because that's where we get our drinking water, but it also induces seepage vertically through the soil. So the groundwater table is constantly moving down, and that affects the stress conditions that we encounter as well. So, okay, so just to review the soil stresses here, let's see if this is actually going to work as a moving thing. Okay, no. So let's say we have this little profile. Again, there's a cross section of the earth. We have a sand layer and a clay layer, and we're going down here with depth. What we're first going to assume is that this soil, this sand layer, is homogeneous. So that means it has the same properties everywhere in it. Now, real world scenario, this isn't the case, right? We're going to have different soil properties with depth. It could be like even just on a couple inches scale, like be different. But for this case, what we're assuming is the unit weight within the sand layer. Sorry, that's a gamma. All the properties, whatever, the void ratio, all the stuff we talked about, it's the same regardless where we look in this soil column. The other thing that we're going to assume here right now is that it's hydrostatic, which means the groundwater table is staying put. There's no moving of water within the soil. So if you were to dig a hole and found the groundwater table, then it would just stay there. It wouldn't move. It wouldn't go up and down, that kind of stuff. So hydrostatic. So let's say we wanted to find a point right there. And again, this is taken from geotech, so it probably looks familiar. But if we were to zoom in on the soil right at that spot, what we would see is if it's a sandy soil, it would look like just a bunch of little rocks, lying on top of each other. And this is because this is a cohesionless, a granule material that we talked about last week on the first week. So we know that all these rocks, the way these are actually holding up by each other are stresses. So again, this isn't going to work. Oh yeah, it did. Okay, cool. So stresses. So if you could picture from like your statics class and stuff, whenever you were doing the distribution of stress through a truss or something, like through a structural element, like on a small scale, the same thing is happening with soil. Like the weight of the soil above it is being distributed through these points of contact through the soil skeleton, and it's being distributed down, and it's hopefully in a static condition, which means some of the forces are equal to zero, the acceleration is equal to zero, there's no movement, and it makes our calculations super easy. But unlike method of joints or anything from statics, like we can't just do an easy analysis of the soil structure. We're working on a large scale, there's too much randomness in that whole thing. So what we do is we analyze the soil mass as a body, and this is really important, or this is why the unit weight is really important. So we're looking at it in terms of relative scales like mass per a unit volume. So what we know is that this skeleton, this like body of soil, however large it is, this set volume, we can just say this is like a set volume, total volume. There's a mass inside of that. That this is acting as a body and it's exerting a force below it on soil similar. And then same thing above it, we have a similar soil mass creating a force and acting on that that's being transferred down. Now, of course, instead of a force, what we're talking about, since we're looking at not just a cross section, but a entire 3D world of soil, we're talking about a stress. So that's where that unit weight or that sigma value comes in, and that's that total stress, the stress acting on the element above from it above it. So if we wanted to know what that point is right here, what that stress would be, what we could do is just add up all of the volume, all the weight of the material above it. Just like water, if the deeper you go, the more pressure you feel. Same with soil, the deeper you go, you're just adding more pressure on top of you. And so at point A, just for example, technically what we're saying is there is a certain height of a material with a set density that is exerting a pressure at that point of A. So this H, for example, let's just say that would be proportional. That larger the H is, the larger the pressure is, the larger the stress is. And if this is homogeneous and that unit weight doesn't change, then we can say that total stress, that sigma at point A, is just equal to that unit weight times the height or the depth at which we are investigating. And if we check the units, we'll see it checks out because we have pounds per cubic foot for our density. And then the H here is just going to be in feet. So what we're left with is pounds per square feet, which is a stress or a pressure. So again, this is another area where the FE or me will try to trick you. If your density is not in the same units as the depth or that H value, then you have to convert it so the stress values will cancel out. So keep an eye for that, especially when you're working and you see an SI problem. Like they'll give you the density in centimeters per cubic, or sorry, per cubic centimeters, and then the height will be in like meters or something like that. They definitely, I think I remember that from the FE. So keep an eye for units there. That's important. So yeah, so this is just the total stress. This probably makes sense to a lot of us who's ever swam in water before. Again, it's same thing with soil. The deeper you go, the more weight you feel at that point. So if we had a saturated condition, then it's a little different. So saturated, especially in Florida, that means all of that void space that we see here is actually filled with water. And so for that, again, these are all filled with water in this case. So we have a water table there and there's no air. And now in this little unit of volume, we also have a weight of water that is filled inside of it. So for that, then we also have to include our weight of water. And we know that this weight of water, again, shows if it's pounds per cubic foot. And again, this is only if it's, just read from before, this is only if it's hydrostatic. Come on. Oops. Yeah. So for this, we not only does our conditions here, the unit weight, since we have the total stress, we would obviously be feeling more because now not only is there soil above us, there's water above us, but us as engineers need to account for only that water pressure. And that is what we would call the pore water pressure. This is also called neutral pressure in some of your textbooks. So you may see that, but most of the time now we're going to call it pore water pressure. So we have the weight from the skeleton, or the total weight of everything, the soil and the water, but then we also have just the water itself. And we'll talk about why it's important just to look at only the water. But the whole point is because, again, that water can change and it can be a dynamic situation where the water has different pressures. But if it is static, then that unit weight or that pressure, that pore water pressure here, U, that's also sometimes just shown as PWP, pore water pressure. In some of the geotech reports, you might see it that way. It'll just be shown as the weight of the water multiplied by the height of the water. So as we see, as the total stress increases, our pore water pressure will also increase, because the more water we're adding, then the more total stress. Like total stress is everything that we're feeling at that point A. So this whole thing to say, like, why is this important for geotechnical engineers, and why will we like study this in more detail throughout the class? If you remember from the first class we were talking about, there's two kind of groups of soil. There's cohesion and then cohesion and then cohesive and cohesionless. For the most part, though, soil is a frictional material. So just like aggregate, you know, it gets its strength from the interlocking bonds and all of that, like distribution of stress through friction. So soil will fail through what we call shearing. And the best way to visualize this is like sandpaper, or like a sandpaper block. So we had a sandpaper block, and just like a sandpaper block, like if you had just a block sitting on here, it'd be easy to push it, right? Because that friction is light. But if you were to stack a bunch of weights on top of that sandpaper and increase the normal weight, then it would be harder to push that. It'd be harder to have that friction, or the friction coefficient would increase because it's proportional to that normal weight. So it's the same thing for soil. So generally, through soil, as that stress increases, as the sigma increases, we'll see the soil strength will increase. But also the resulting load from the soil will increase, which will have its own issues. But this is why that stress is really important, because that stress is normally proportional to the strength of the material, because its resistance to shear will increase. Let's talk about how to calculate the total stresses then for that case. So again, same case scenario, we have point A, and generally what you'll see as we're showing these profiles of a site condition, like whatever, like you're about to construct or design, then what we'll have to do is provide the profile of everything. So in this case, the groundwater table again is shown by this. We're at the surface here. So we're going to assume our sample is saturated. So the density through everywhere is going to be our gamma saturated. So for that, our total stress again is just going to be our weight felt at point A. So what we're going to have to use for this is our saturated unit weight. And we just multiply that by H, since again, this material is homogeneous and that's the same properties everywhere in the sample. So if we were to do that at point A and plot that, then obviously it would just be a single point there. Since we're not changing gamma, if we use half of an H, then it would just be half of that value. So you can see this is just a linear relationship. So this should just be a straight line, super easy. And of course, this will change, this graph will change if we change our saturated. So in some cases, you may see different soil layers with different properties. And if you remember, then these soil properties, this won't be a perfect straight line. It could change and have different segmented. So we have that. Let's find our pore water pressure. Again, pore water pressure or the neutral pressure. And this is shown by a U, and that is the unit weight of water. Again, then unit weight of water is 62.4 pounds per cubic foot. That's multiplied by the height. So right here, since that height of water is H as well, since it's at the surface, it's going to look very similar. We find that first point at point A, and then we could do however height above it, but we'll see that that is just a straight line too. So this is fine, but when we're actually designing, like what we know about the water is the water can change, right? So in some seasons, the water table might be at the surface. There might be a bad drought. Some farmer might come and pump and lower the water table, and that water table could dump down. So if the water table in this little example goes below that point A, what's going to happen to the stress in this case? You know, we're no longer using the gamma saturated. What we're going to be using is just the moist unit weight, because most likely there's going to be air now in our sample. And we know that then if we're changing this value here, then our total stress is going to be different, because now we're removing the water. So our total stress is going to be lower since we're removing that water. So if we were designing on that total stress, then we would have issues, because now this soil does not have the strength that we thought it did. Again, remember this stress here, generally as stress increases, the soil strength will increase. So what we need to do, instead of using total stress, since the pore water pressure cannot be trusted because it can change, the H specifically can change, the height of the water. What we use instead is a term called effective stress. So what we do is apply a very serious math equation. We subtract the pore water pressure from the total, and then we put a little line on top of it, and we call that the effective stress. And this is super helpful and super easy. And this is what we generally will design for when we're correlating the stress with the strength of the soil. A lot of times, you know, if you're not used to seeing this, you know, it can be easy to miss the little prime. But that little prime, the little apostrophe at the top, that has a completely different value because we subtract the pore water pressure out. So again, the effective stress is what you'll see most of the time is going to be the most important parameter, and that's the total stress subtracting out the pore water pressure. And it's easier for me if I think about like what this physically represents. You know, you see it as an equation, you're just like, okay, cool, this is what we calculate. But what it actually means in a granule setting is what it is showing is the intergranular stress. So if you remember from our little picture, the zoomed in soil there, all of the connected points there, that stress actually being felt from those two connection points is what we're actually calculating this effective stress. So if you were to actually do all the math and all the fun, you know, stuff from physics is equal to 0, assuming it's in a static case, what you'll see, and you don't have to worry about this, but what we'll see is it all checks out and we end up getting this equation here where our total stress is equal to this intergranule stress plus the pore water pressure that's being felt. So on the other side of things, if we were to rearrange this and then we only care about the skeletal stress, that intergranule stress, then it would just equal the total stress minus the pore water pressure. Again, this is the safer thing to design against because that pore water pressure could change. So if you're designing a project for 160 years or whatever, and then obviously the groundwater conditions can change. If you're designing it for the total stress and we lose the pore water pressure, we lose strength, then it could fail because we don't have that extra accountability. So we want only the intergranules or like the grains to carry the loading from the structure above or whatever. So this is for like granule, for cohesionless soil. You remember though, we were saying another type of soil is fine grained soil, the clay. This is generally the cohesive soil. So what this physically represents is a little bit more tricky. If you remember, clay material is super, super small. It's basically just a bunch of plates sticking on top of each other, so they can't be just visualized as small little rocks. So this is an issue because they are actually physically not touching. So the mineral crystals don't have any physical contact since they're actually being supported by these electrostatic forces that are separating them, almost like little tiny magnets. So we can't really do the math between the intergranule stress, like we can't follow the skeleton of these rocks touching each other. So there's a lot of research and there's a lot of people like spending a lot of time trying to figure out what the effective stress physically means in clay soil. But the thing that this really important geotech dude, Skempton, found in 1960, he said basically like from empirical evidence, this effective stress still counts for sands and clays when they are 100% saturated. So if whatever reason you end up doing like a PhD or you ever end up like teaching and or just for some reason like COVID 2022, like you decide to go really deep and just learn a lot about geotech, you'll see there's a whole other side of unsaturated soil mechanics, like partially saturated soil mechanics. And that's actually more difficult because this assumption of effective stress doesn't hold true when it's unsaturated or partially saturated. So for us, we're just going to assume like clay is always 100% saturated, and we're never going to really worry about partial saturation when we start getting into the like the mechanics behind it and stuff. Is this ringing a bell to everybody at least who took geotech? Cool. Okay. All right. So let's look at a few examples of how to calculate the total stress, pore water pressure, and effective stress at elevation A. So that's this part right here. What we're told, again, you need to keep an eye out for this little cool triangle with lines underneath it. This is telling us where the groundwater table is. So the groundwater table is right at that point A, but we're told that the soil is still saturated. So the density, so this is the same as unit weight, except it's just the density. Right, so that's similar. We're just in SI units, so we're using density. If you remember, just as a recap, it's just equal to this times gravity, the gravity coefficient, density times the gravity is bulk unit weight, as we go from a force, or sorry, a mass to a weight. But anyways, what the simple example, we could just see it as like a column column of soil, and we want to find the stress at the bottom of it. So what we're told here, we're told that first we're assuming again that this is hydrostatic. There's no movement of water. This groundwater table is staying put. And to find the total stress, go back to red. Find the total stress, we're just looking at everything that is above it. So what we see here, since again, we're using density instead, this is technically times G times H. So a recap too, mega, uppercase M, this is same as million in SI. So mega, million, that's 10 to the 6. So that would be equal to 1 million grams per cubic meter. So again, like even if you're planning on sticking around in the States and you're planning on just, only working and not like doing any research or anything like that, like the FE and the PE will have units in SI. So don't forget about them, try to still sharpen them, especially when you take those tests, and then you can forget about them if you want. But keep in mind that, because you will see that through the semester too. But another thing to remember here, let me just write it up here actually. A Newton, because it's kind of tricky going from forces and weights. A Newton is equal to 1,000 grams time meter per second square, or 1 kilogram meter per second squared. So that would mean, or another thing that's important is 1 kilopascal, which is a pascal is a Newton meter per, or Newton per square meter. So it's a stress that is equal to 1,000 newtons per square meter. So you'll see that in stresses a lot. A kilopascal is a unit of pressure or stress, same thing. It's a force per area. So kilo, 1,000, and then a pascal is a Newton per square meter. So keep that in mind too. And yeah, if you're unfamiliar with those. Okay, so back to the problem here. So we have most of the stuff we need. We know that this is 2 megagrams per cubic meter. The G, the gravity acceleration constant, is 9.81 meters per second squared. And then H is 5 meters. So if we cancel all those out, you're going to have to get it. The goal is to get it into like a kilopascal. What we'll see is at this point, the total pressure that we're feeling is 98,009, whatever that number is, Newton square meter, which conveniently equals 98.1 kilopascals, right? K 1,000 Pascal Newton per square meter. So that's our total pressure. What would be the pore water pressure at this point? Yeah, so I think I heard somebody say it. We know that this is times the H, the height of the water above it. So in this case, it's 9.81 kilonewtons per cubic meter. That's the density of water, or the unit weight of water. And then the HW, the height of the water above it, it's at that point. So this is 0 meters. Everything cancels out. So the pore water pressure is going to equal 0. So again, just like pore water pressure, what you can think of is if you were swimming. If you were at this point, the pressure on your ears due to the water would be 0 because you're not underwater. You're just chilling at the surface. As soon as you start going underwater, then that pressure is accumulating because the height of the water above you is increasing. So for this case, the effective stress is pretty easy to calculate because there is no water conditions. And this is our total stress. Then we subtract out the pore water pressure. So that's just 98.1 kilopascals. Make sense so far? Cool. All right, so in this case now, let's say we increase that water table up to 2 meters above the ground surface. So this is all water here. And now we have like a so our total for this case would be everything that is like being felt at this spot. So again, like if you could feel all of the pressure right here, what we would have is that weight from the soil, which is what we found before. But now we're also adding the weight of this water above us. So again, think of it as like a free body diagram, like what we're seeing at point A, we have that weight of the soil above us, but we also have the weight of that standing water added too. So just as before, for this part, it's going to be 2. I'm not going to include the units this time just to keep it simple. Times 5 meters, since that's the weight of the soil, and then the weight of the water above that is going to be 9.81 times 2 meters. This is going to be a little bit higher, 117.7. Again, this makes sense because we're adding more material, so our total weight should be, or our total stress should be higher since we're adding more material this time. So the pore water pressure this time, because remember this is the unit weight of water times the height of water. So now at point A, that water table is this. So this much water is what we're feeling. So now we have 9.81, which is the unit weight of water. And then times the height of that water is 7 meters. So it's not just 5. Again, if we were to dig a hole through this soil, we would see the whole thing fill up with water. So that height of the water is going to be 7 meters. That's really important. Don't just do 2 meters for that case. It's easy math here. That's going to be our pore water pressure. So as soon as we find the total pressure and the pore water pressure, we can find our effective stress. And then this is just equal to 117.7 minus 68.7. So 49 kilopascals. Yeah. Yeah. So the reason why is because this saturated already includes the water within the pore space. So like thinking about like the circle that we're talking about, that circle volume, it's not all water, it's solid and then water. So that's already included into that. Yeah, that's a really good question though, because I remember
the saturated then times 4. It didn't have the water.
Times what? It did. So this soil can still be saturated. That's what it was saying here. Yeah, it's just not submerged. Yeah. So still, if we were to zoom in here, you know, you would see the soil grains and the water. And this is really common in clay. Like sometimes the water table can be below the clay level, but because of capillary rise, if you remember that from geotech, the pore space can still be filled with water. So this is really common in a clay like material. You might see that. Okay, so just to compare these so we can get an idea of how that groundwater table changes. For our submerged case, these are the 3 values we got. And then for our saturated case, even if we have the same, density here, the groundwater table, we can see it's almost half of the effective stress. So although the total stress increased, that groundwater table plays a big role. So if we were designing just off of this value, we'd be like, okay, good. Like the water table goes up, we're good. But then if it goes down, then we are obviously losing that stress value, and then that changes our strength. That's why we always will design for the effective stress down there. So again, this is just a single soil column, but most of the time what we'll see is an example like this where we have different stratigraphy. So stratigraphy are different soil layers with depth. And as a geotechnical engineer, your first job is going to be to define these soil layers and then be able to do the analysis on it. So in this is a common example like in Florida where we have sand, we have a water table right here, and then we have clay underneath that. So let's say we want to find the total stress. Again, that's sigma with pore water pressure, and then the effective stress at this point A down here. Again, zooming in here, what we have is like thinking again, this would be the gamma sat that we're using because there's water inside of it. Gamma sat, what we're using, but then for the sand, we're not told that it's saturated. So we're just going to use the normal unit weight above that water table. So the total stress at A, let's see if I actually wrote all this stuff down so I don't have to go through it at all. Okay, yeah. So again, we're just thinking about like what we're feeling if you were to be a little piece of sand at point A. You would have 4 feet of a material that's 95 pounds per cubic foot. And then you would have 2 feet of a material that is 112. And then you would have 2 feet of a material that is 105 pounds per cubic foot. So if you were that sand particle, that's what you would have to hold up at that point A. So how you would find that then, you just multiply each one. You could find the stress contribution from each one and then add them all up to get the total stress. So the total stress at that point is 814. So again, total stress is just everything that is above you, you add it up. The pore pressure at A is going to be, again, we're assuming hydrostatic in this case. This height of the water here. So this is 6 feet, 4 plus 2. And then with that material is 62 pounds per cubic foot. So our pore water pressure is 34 or 374. And then of course our effective stress, because we can't trust the water here, we subtract those two out. And that's 439.6 from this minus this. So that's important. Again, this is a hydrostatic case, but as I mentioned before, there's many times that we may have a flow of water vertically, and that's going to affect it. So if we had a water flowing instead, so we don't have hydrostatic cases this time, what is going to happen now is it's going to affect our pore water pressure. So in order to have water flowing or a change of water pressure, that would mean we have a change of head. If everyone remembers from fluid mechanics, if you've taken fluid mechanics. So what we would show is technically if we had water flowing down, what that would mean is the pressure at point A would be lower than the pressure above it, right? Because water is always trying to equal out pressure. So if we were to stick a tube down at point A, the water would only fill up to this section here. And that would mean the higher head, the higher pressure is trying to equal out with the lower pressure. So the water is going to travel from a higher pressure, a higher head to a lower head. And that is going to cause the seepage vertically like we see here. And this is, most area in Florida is like this because the aquifer is at a lower pressure. Area where it's not, you see the springs and all that fun stuff in Ocala and Gainesville and stuff. But most of the area of Florida, we have a downward seepage of water. So for this case, we can't have this because we no longer have 6 feet of water. Our new height of water is lower, right? And there's just arbitrary here. I'm just going to say it's a lower value. So that means our pressure will be lower. So if our pressure is lower, that means our effective stress is going to change. And our effective stress will actually increase. So we're going to have an increased situation. So it kind of makes sense vertically. Again, like if you think about what's happening on the intergranule level, if you have water flowing from top to bottom, it's going to add more pressure and cause those grains to come in contact more with each other. So our effective stress will increase. If we have the other way around, and instead now we have water going from point A up, that would mean that our pressure at point A is higher, that head, that HW is no longer less than 6 feet, it's greater than 6 feet. So here, it's kind of hard to see there, but our HW now is greater than 6 feet. So now that would mean our pore water pressure is going to increase since we have greater than 6 feet of an HW. If we increase our pore water pressure, again, our total stress stays the same here since we're not adding any material, we're just changing the water flowing. This would mean that our effective stress will decrease. And if you remember from the geotech side of stuff, there's a special like issue that would happen if our effective stress, those grains touching each other, if that equals to 0, then we have what's called our quick conditions or liquefaction conditions. And this is basically like quicksand and stuff, if you remember any of that stuff. I think I have a video here, but this is a big issue anytime you're designing dams, anytime you're working with any type of water flowing. You do not want quick conditions because the particles are not touching each other anymore, so it can't support any weight. It just pretty much acts like a liquid. So that's just the general trend if there's seepage, but if there's more examples, just if it's a hydrostatic, if we have the groundwater table at the surface. Let me just fill out these real quick. Since we're running out of time, the total stress again would be what we talked about before. Oof. So we would have 4 times 95 from this soil layer. We would have 2 times 112, 2, and then this one right here. We would have 2 times 110. And all of that would then be added to 824 pounds per cubic foot. So this is our total stress at A. Pore water pressure at this case If it's at the surface, this is our HW. So we have 8 feet of water. So this is 8 times 62.4. That's equal to 499. This is our U. So effective stress here, 824, 499 is equal to that. And this is when it's at the surface. So if we were to increase it, like if you had a flooding scenario, and now we have 3 feet of water above us. So this is, standing water. Some guy with a boat there. Then that would change our total stress. So not only will we use the saturated, but now we're going to have another material of gamma water here. So again, just as we said before with these 3 layers, now we have a 4th one here. First layer will still have the 4 feet of 95 pounds per cubic foot. Second one will be 2, 12, will be 2, 110, and then the 4th layer is the water layer. We'd have to add that as well, the 3 feet of 62.4. So this is all equal to now 1,000 whatever PSF. This is our total stress. A, still A. Our pore water pressure. Now we have 11 feet. That's our HW. So this no longer equals 499, but now it equals 686. So our effective stress is now going to be lower 324, 325. So to summarize all this, what we'll see is the reason why, I'm stressing all this stuff and going through all this is when you're working as a geotech, the groundwater table is going to change a lot, and we need to account for these situations. So working with geologists is important, but working also with FEMA, knowing that if the area is going to flood, working with farmers nearby, knowing if they're going to pump and lower the groundwater table, because we'll see the in situ stresses changes a lot. As a trend, as the groundwater table increases, so it gets closer to the ground surface, the effective stress will decrease. And that is generally an issue, right? Our effective stress is we show equation wise, this is not going to change. But what we're doing is we are increasing our pore water pressure. So as we increase our pore water pressure, as we increase the pressure head, the water, then we increase our pore water pressure. And as we increase our pore water pressure, then we decrease our effective stress because we're subtracting more from something. So as the groundwater table, sorry, I think I messed that up. Oh, no. Yeah, this is right still. So as it increases above the ground surface, so if we have flooding, the effective stress stays the same actually. So the reason this is because we are adding the same thing to both cases. So we are adding the same HP to our total stress as we are adding to our effective stress. So those cancel out, and any increase in pore water pressure is equal to the same increase in total stress. So on the other side of things, as the groundwater table decreases, so it gets deeper and deeper, it's drawing down, then the effective stress increases. And again, this is intergranule stress that we're talking about. So as the stress increases, the soil strength increases, which is good, right? Because it's a granule thing. But we also have issues where the resulting load from that soil increases. And so the pressure on the soil increases. So I shared an example in geotech class, but like if you think about it, like what's actually happening, it's being squeezed and that stress is greater, so it's actually compressing a little bit, and it can cause a lot of settlement. There's a town in California where they've just been lowering the groundwater table because of all the farming, and as that groundwater table is lowering, the effective stress is increasing, and it's actually causing the soil to compress almost like a sponge, and the whole town has settled like over like 15 feet since the 70s or something. So it's like literally the whole soil mass is just being compressed and compressed. And it's just because of the dewatering. So groundwater is really crucial in geotech, and it plays a lot into the strength of the soil and the general mechanics that we'll see. I almost want to wait to get into this just since we've been talking for a while, and this is kind of important going forward. So we'll catch up here after. I'll show all those cool little pictures after, but just let me get to the last slide. Since we only had one class this week, yeah, we'll pick up on Wednesday. There's no quiz this week. What you will see is I'm going to repost these lectures notes next week, starting on that last slide. So you can either keep the ones you just downloaded, or you can re-download the next one, and it'll just pick off at that same point. And again, I'll post the recording of this lecture on Friday around noonish. So if any of this is weird or you don't get it, or it's just completely new to you, then let me know, send me an email, we can meet, because I'm not giving it a lot of time going over this because we need to get moving forward. Enjoy the rest of your week, guys. We'll see you all next Wednesday or next Monday.